Hello and welcome to today's lesson looking at forces in braking. In today's lesson, which is part of the AQA Combined Science specification, we're going to be looking at forces in braking. So we're going to try and understand the force of an object when it's braking. So we're going to try and understand what stopping distance is and state various stopping distances, detail the factors that affect stopping distance, and finally detail the work done when a braking force is applied to a moving object. Now this sits in the following part of the AQA Combined Science course for physics in the forces module. So in this lesson we're going to be focusing on stopping distance, reaction time, and the factors that affect braking distance for an object. So consider a moving vehicle such as a car. If we wish to stop the car from moving, we must place a braking force on the car. Now this is a resultant force used to decelerate the car to a stop. Now remember, a braking force acts against the motion of an object. So in this example, for a car, the braking force is going to come from the frictional force between the brakes and the wheel and the air resistance. Now, the braking force needed to stop a vehicle in a certain distance depends on the following. The first factor is the velocity of the vehicle when the brakes are first applied, because the greater the velocity, the greater the deceleration, which is a negative acceleration, needed to stop the vehicle, so the braking force must be greater. We know this from the equation of Newton's second law of motion, F equals ma, because the greater the deceleration, so the greater the a in the equation, the greater the braking force, or F in the equation, for the same mass. Now the second factor that affects your braking force is going to be the mass of the vehicle, because the greater the mass, the greater the braking force needed to bring the object to a stop. Once again, this comes from the equation F equals ma, Newton's second law of motion, because the greater the mass, or m in the equation, the greater the braking force, or F in the equation, for the same deceleration, a. So, just to clarify before we move on, there are two factors that affect the braking force needed to stop a vehicle in a certain distance, and those are the velocity of the vehicle when the brakes are first applied and the mass of the vehicle. Now both of them, but the greater the value, the greater the braking force required, which is shown from the equation F equals ma. Now, this leads on to another concept, which is called stopping distance. Now, stopping distances show the shortest distance a car can travel once you've seen a hazard in the road to when you stop moving. Now, they're very, very important, so it allows you to judge how far you would travel if you broke at a particular speed to see if you would crash your vehicle or you would knock someone over. So it's very important you know your stopping distances. Now, here are some general guides to stopping distances for vehicles on UK roads for different speeds. Now, whilst you don't need to be aware of this for your GCSE examination, this does need to be memorised for your UK theory driving test if you wish to pass it. So when you're studying from your driving licence, you need to be aware of the different stopping distances for different speeds. But we split the actual distances into two categories. So just to clarify, the stopping distance of a vehicle is the sum of the distance the vehicle travels under the driver's reaction time and the distance it travels under the braking force. So this leads us to two particular ideas: the thinking distance and the braking distance. And we can say that stopping distance is equal to thinking distance plus braking distance. So for example, if the thinking distance was 20 meters and the braking distance was 45 meters, the stopping distance will be 65 meters. Again, if the thinking distance was 30 meters and the braking distance was 55 meters, the stopping distance will be 85 meters. And finally, if the thinking distance was 40 meters and the braking distance was 75 meters, your overall stopping distance will be 115 meters. Now, the thinking distance is the distance the vehicle travels during the driver's reaction time. Now, a driver's reaction time can be affected by tiredness, by taking drugs, or drinking alcohol. Now, distractions can also affect a driver's ability, such as people talking to them, such as people texting on their mobile phones. Now, the reaction time for a person does vary. There's no one set reaction time for a particular person, but the typical reaction time for a human being varies from 0.2 seconds to 0.9 seconds. Now, the braking distance is the distance the vehicle travels under the braking force. Now, the braking distance of a vehicle can be affected by adverse road conditions, weather conditions, and the poor condition of the vehicle. Now, adverse road conditions include wet conditions or icy conditions, but you only have to be aware that the poor condition of the vehicle is limited to either the vehicle's brakes or the vehicle's tyres. Now, as mentioned previously, the braking distance and therefore the braking distance so the braking force and the braking distance it generates is affected by the mass of the vehicle and the deceleration of the vehicle. Now, this is very important because the speed of the vehicle will affect both the thinking distance and the braking distance. And the higher the speed, the higher the thinking distance and the higher the braking distance. Now, the higher the speed, the greater the distance traveled for the same reaction time, so it gives you a bigger thinking distance. Now, speed and thinking distance increase linearly with each other as reaction times tend to stay fairly constant for a human being. So if you are just traveling faster, your thinking distance will increase at the same rate. Now, the higher the speed, the greater the distance traveled for the same braking force, so therefore the greater the braking distance. However, the speed and the braking distance increase at a faster rate compared to the speed and the thinking distance, as the brakes are transferring energy from the kinetic energy store. And we know we can work that out from the equation a half mv squared. So what this means is, as the speed increases, the work done and therefore the braking distance increases by a square of that increase factor. What I mean by this is, as the speed doubles, the work done and therefore leading onto the braking distance increases by a factor of 4, 2 squared. And again, as the speed triples, the work done and therefore the braking distance increases by a factor of 9, 3 squared. Now, speed limits are really important as the speed affects the stopping distance so much because it affects both the thinking distance and the braking distance. But also remember, why do we need to calculate the stopping distance? Well, to avoid an accident, drivers need to leave enough space between the car and the one in front, so if they have to stop suddenly, they will have enough time to do so safely, which leads into your concept of your stopping distance. So let's just clarify. The shortest distance it takes for a moving vehicle to stop after spotting a hazard is the stopping distance, which is affected by two factors. The distance the car moves when an observer observes a hazard, to press the brake, is the thinking distance, whilst the distance the car moves after the brake has been pressed until it stops moving is called the braking distance. And we know the stopping distance is equal to the thinking distance plus the braking distance. Now, when an object, such as a car, is moving, they are decelerated, as we said before, by placing a braking force on the object. So a resultant force is placed on the car from the brakes. So a resultant force, as we've learned previously, will cause a deceleration. So as a result, we know this because F equals ma. So if we put a resultant braking force F onto our particular object with a mass m, it will produce a deceleration or negative acceleration of a. Now, we also know that a resultant force, as well as causing an object to change speed, also causes energy to change type of store in the system. So here, the resultant force is the friction between the brakes and the tyres. So we say work is being done in the system, or work is being done by the friction force between the brakes and the wheel. So what's happening is this resultant braking force is making the object do work as it's making the kinetic energy store of the car change form. So what's happening is that when this resultant braking force is applied, work done by the friction force between the brakes and the wheel reduce the kinetic energy store of the object, and this energy is transferred to the thermal energy store of the brakes, and the temperature of the brakes increase. So as the energy store is changing with the resultant force, we say work is being done. So when there's a large braking force applied to a car, the car's brakes will glow red because it's now a large thermal energy store. So the brakes have a very high temperature. They're very hot. And you can see this on certain race cars, for example, where you'll see brakes glow red when they're near a corner. Now, basically, over time, the thermal energy store of the brakes is then dissipated to the internal energy store of the surroundings. Now, remember, the larger the deceleration, the larger the resultant force needed to decelerate, so more energy is transferred to the thermal energy store of the brakes, and the brakes get hotter and hotter and hotter. Now, That's very important because if there's a large enough deceleration, because you need with a large enough resultant force, the brakes will contain so much thermal energy because this force is so much larger, causing lots of work to be done, they'll actually overheat and set on fire. And you can actually again see this on racing cars and Formula One cars, that occasionally brakes will set on fire. So you can see it here in this particular GIF, okay, showing the actual brakes on fire for this particular racing car. So, the greater the speed of a vehicle, the greater the braking force needed to stop the vehicle in a certain distance. So the greater the braking force, the greater the deceleration. Now this is very important because large decelerations lead to brakes overheating, as mentioned before, and a loss of control as well. So this can actually cause a car to skid, as shown by the following particular animation here. So the large change in energy store causes the car to lose traction with the road, which causes a skid. Again, shown in this particular example, so you can actually see the car start to skid. And we need to be able to estimate the magnitude of the force which causes these decelerations. Now this can be done by combining two particular equations. You use your equation of motion equation we looked at previously, so v squared minus u squared equals 2as, to work out a, the deceleration of the object, and then you place it into the equation F equals ma to find the resultant force of the brakes. So let's just clarify what we've learned there. So when a force is applied to the brakes of a vehicle, work is done via friction between the brakes and wheel to transfer energy from the kinetic energy store of the vehicle to the thermal energy store of the brakes, which then dissipates to the internal energy store of the surroundings. The greater the braking force, the greater the deceleration, and large decelerations may lead to brakes overheating and a loss of control for the vehicle. So that's very, very important. So let's see if we understand what we've covered so far. So friction and air resistance oppose the driving force of a car. The stopping distance of a car depends on the braking distance and the thinking distance. High speed, poor weather conditions, and poor maintenance all increase the braking distance. Poor reaction time and high speed both increase the thinking distance. Now, reaction times vary from person to person. Typical values range from 0.2 seconds to 0.9 seconds. A driver's reaction time can be affected by tiredness, drugs and alcohol, and distractions may also affect a driver's ability to react. The braking distance of a vehicle can be affected by adverse road conditions and weather conditions, along with the poor condition of the vehicle. Now, adverse road conditions include wet or icy conditions, and the poor conditions of a vehicle are concerning the vehicle's brakes and tyres. Finally, when a force is applied to the brakes of a vehicle, work is done by the friction force between the brakes and the wheel, reducing the kinetic energy stored in the vehicle and increasing the temperature of the brakes. The greater the speed of a vehicle, the greater the braking force needed to stop the vehicle in a certain distance. And finally, the greater the braking force, the greater the deceleration of the vehicle. So large decelerations may lead to brakes overheating and the loss of control. I hope you've enjoyed this particular lesson where we've looked at understanding what stopping distance is, and we can state various stopping distances. We can detail the factors that affect stopping distance, and we can detail the work done when a braking force is applied to a moving object. And that is the lesson on forces and braking for the forces module for AQA GCSE Combined Science. Thank you and have a lovely day.